In a world with no bosses, no central service telling everyone what to do, how can anyone possibly trust anyone else? It's like the fundamental challenge of any peer-to-peer network. So today, we're going to dig into how one system, GenosDB, solves this with a model that is surprisingly elegant. Let's see how they pulled it off.
So, here's how we're going to break this down. First, we'll get a handle on that core trust problem. Then, we'll dive into the 3 cryptographic pillars that GenosDB is built on. After that, we'll meet the local enforcer. Think of it as a referee. We'll even see it in action against a cheater. And then finally, we'll put all the pieces together to see how you get real security without a central server.
All right, let's jump right into Section 1, the P2P trust problem. This is really the nut that every decentralized system has to crack. I mean, think about it. In a network where everyone isn't equal, who gets to make the rules? And maybe more importantly, who's going to make sure everybody actually follows them?
This really is the million-dollar question, isn't it? When you don't have a bank, or a company, or some big server in the middle acting as the referee, you're just left with a bunch of strangers connected to each other. So, how do you stop it from becoming total chaos? How can you be sure the person you're interacting with is playing fair?
So how does GenosDB solve this huge problem? Well, their answer isn't to just build a new kind of central server. Nope. Instead, they built the foundation of trust directly into the network itself, using 3 really powerful cryptographic pillars that every single person on the network has to agree on.
And here's the absolute genius of how these 3 pillars work together. First, your Ethereum address. It's basically an unforgeable passport. No faking it. Second, every single thing you do is digitally signed. This creates a rock-solid, undeniable record of who did what. And third, and this is the real kicker, everyone has the exact same rulebook, this shared constitution built right into their software. It's like playing a board game where every single player has their own copy of the official rules. You can't just make up a new rule in the middle of the game and expect to get away with it.
Okay, but having a rulebook is one thing, but actually enforcing it, that's a whole other ballgame. And that brings us to our third section, the local rule enforcer. We're about to meet the very clever piece of the puzzle that acts like a dedicated referee on every single machine in the network. So meet the security manager, or SM for short. This little piece of software is really the unsung hero of the entire system. It lives on every single node on every computer in the network, and its one and only job is to be the bouncer at the door. It checks the ID and the invitation of every single command that tries to come through. What makes the security manager so powerful is that it's just incredibly paranoid, and that's its superpower. It trusts absolutely no one by default. It doesn't care if a request comes from your best friend or a complete stranger. It demands verifiable, cryptographic proof for every single action, every single time, no exceptions. All right, so this all sounds great in theory, but the real test is how it holds up when things get messy, right? That's what Section 4 is all about, stopping a cheater. Let's cook up a little scenario here and see what happens when someone actively tries to break the rules. Okay, so here's Eve. Right now, she has guest-level access to the network, which is pretty limited. But Eve is, let's say, ambitious. She wants the power that comes with being a manager, and she's not about to wait around for a promotion. So, Eve gets clever. She creates a command that says, promote Eve to manager, and she sends it over to another user's node. Let's call her Alice. Now, Eve could even modify her own software to make it look like she's a manager on her own screen. But here's the crucial part. That little trick doesn't matter to anyone else on the network.
And bam! This is exactly where Eve's master plan just slams into a brick wall. When Alice's computer gets that command, her security manager instantly goes to work. First, it verifies the digital signature. Yep, it says, this is definitely from Eve. But then it pulls out its rulebook, that shared constitution, and it asks a simple question. Does Eve actually have permission to promote users? The Constitution checks her role, sees she's just a guest, and knows the guest can't do that. So the result is simple. Permission denied. The operation is just flat-out rejected. End of story for Eve. And this really gets to the absolute heart of the system. In GenosDB, you can't just declare you have power. It doesn't work that way. Your authority has to be proven with cryptography, and it has to line up with that shared rulebook. What you claim on your own is completely irrelevant. What the network can verify is everything. So now that we've seen the system defend itself up close, let's zoom out for our final section, security without a server. We're going to connect all these pieces and see how they create this incredibly robust web of trust that has no single point of failure. But this brings up a bit of a chicken and egg question, right? Like, who grants the very first permissions?
The system solves this by hard-coding a list of superadmins right into its initial setup. They are the designated starting point, the ultimate source, creating that verifiable root for the entire chain of trust that follows.
So let's just recap the whole process one more time. Step 1. Your identity and all your actions are locked down and secured by your private key. Step 2. That shared constitution makes sure everyone is playing the exact same game by the exact same rules. And step 3, that little paranoid security manager on every single computer acts as its own independent referee, constantly checking every single action against those rules.
And that brings us to what I think is the most powerful idea here. Trust in this system isn't handed down from on high, it's an emergent property. It literally just bubbles up from the interactions of all these independent peers, where each one is constantly verifying the others. You get a trustworthy network made of people who don't actually have to trust each other at all. It's brilliant.
And this all leaves us with a pretty fascinating final thought to chew on. When you can build trust directly into the code of a network itself, when you can just remove the need for these expensive, slow, central gatekeepers, what does that unlock? What new kinds of organizations, collaborations, and truly peer-to-peer projects could we build on a foundation like this? The possibilities are pretty mind-blowing.